Hello everyone, I'm Wei Jiang, a PhD student from the University of British Columbia. Today, I'll present our work, COTR, Correspondence Transformer for Matching Across Images. This is a joint work with Edward, Yan, Andrea, and Kwang. Image correspondence is a fundamental problem in computer vision. It tries to answer the question, where does this point go in the other image? Traditionally, there are two streams of methods, sparse methods and dense methods. Sparse methods first detect a bunch of key points, then compute a descriptor or local feature for each key point. Then feature matching is applied to obtain the final correspondences. The sparse methods usually provide a set of sparse matches with high spatial accuracy. It is an important building block for structure from motion systems. On the other hand, dense methods directly predict a displacement field given an image pair. They can predict the correspondences for all the pixels in the image, but usually suffer from low spatial accuracy under strong perspective or illumination changes. We present COTR, which answers the correspondence problem directly. Given an image pair and a query point, it directly predicts the corresponding coordinate in the other image. COTR can solve multiple motions, including camera motion as shown in red, multi-object motion as shown in blue, and object pose change as shown in green. To solve the dense correspondences, we can simply feed all the pixel locations of the image to COTR. Then we can obtain the dense correspondence between the image pair, and we can use it to warp the right image on top of the left image, as shown at the bottom. The architecture of COTR is simple. It has two major components, a CNN backbone and a transformer. First, we use a ResNet to obtain the deep features of the input image pair. Then, we stitch the two feature maps side by side and add a 2D positional encoding to the feature maps. Then, we feed the feature maps to the transformer encoder and let the transformer relate all the features spatially to solve the ambiguity problem caused by the self-similarity. After that, we feed the output from the encoder together with the query points to the transformer decoder. This step will translate the query points into the coordinate space of the other image. Finally, an MLP is used to bring the high-dimensional coordinates to the XY representation. Notice that the input to the CNN is always at a fixed size in our implementation, and it will limit the spatial accuracy we can get. To obtain highly accurate correspondences, we introduce a recurrent zooming in strategy at inference time. The idea is that we can crop a smaller patch around the predicted correspondence and solve the correspondence problem again by looking at the cropped regions. By doing so, we can hierarchically process high-resolution images and also filter out correspondences that are not reliable. Notice that we also use the patches at different zooming in scales, as shown in red boxes, to train the network. We analyzed the effectiveness of the zooming in strategy and find it significantly improves the spatial accuracy. The red curve shows the arrow histogram when the whole image gets resized to a fixed size, while the pink curve shows the arrow histogram when we zoom in 10 times, which means the network can check every details of the original image. As the curves are shown, when we zoom into the image, the arrow distribution shifts to the left and gets squeezed, yielding more accurate estimates. We also introduced two inference time filtering strategy to filter out unreliable predictions. First, we filter out the points that drifted during zooming in. It means the network thinks the previous prediction is wrong. Second, the prediction should be cycle consistent, which means if we feed the predicted result back to the network, It should return the query point, and if the point doesn't satisfy the cycle consistency, we also reject it. One problem we faced is the training data. Traditional optical flow dataset like Kitty doesn't have enough variance in terms of perspective and illumination changes. We utilize the MegaDepth dataset. Although it is designed as a depth map dataset, we found it can also facilitate the correspondence training. By projecting the depth from one image to another image, we can obtain a dense correspondence map between the image pair. Once we have the training data, the training is very straightforward. We used two loss terms. The first one is the correspondence loss, which enforces the prediction to be correct. Another loss is the cycle consistency loss, which enforces the prediction to form a cycle with the query. Here are some qualitative results on sparse correspondences. COTR can predict correct correspondences even with large scale and perspective changes. Here are some quantitative results on the image matching challenge. Our method with 2K correspondences has better performance than superpoint plus superglue without semantic masking. And COTR is still competitive with as few as 500 correspondences. Here are some qualitative dense correspondence results on Kitty. The left column is one of the input images. The middle column is the predicted dense flow, and the right column is the arrow map. Notice that we've never trained COTR with Kitty, and we don't have the ground truth correspondences for the moving objects in the MegaDepth dataset. However, COTR generalized quite well to the driving scenarios. It can build correspondences for the moving cars, even when two cars meet each other, as shown in the red boxes. Here we show the quantitative results on the dense correspondence datasets, like ETH3D and Kitty. COTR also achieves SOTA performance compared with other dense methods, and shows far less performance degradation when the frame interval increases in ETH3D dataset. We also trained a variant that replaces the transformer with MLP. However, the MLP variant has a hard time producing complex transformations as shown in the dome in the second row. The MLP variant can't move the dome from the right to the left, while the transformer version is able to do so. This shows the importance of having a transformer in the architecture. Our hypothesis is that the attention mechanism in the transformer allows it to model long-distance complex transformation, while MLPs tend to produce simple global transformation. Here we apply COTR to an object-centric scene. COTR is trained with static scenes, but it can handle multi-object motions, such as this example, where the bottles are swept. This is our demo video. We use COTR to track the four corners of the paint and replace the original paint with a virtual paint. Here, we predict the dense correspondences between two calibrated views and triangulate the 3D point cloud. It successfully reconstructed the building. Also the Sphinx. With only two calibrated views, we can already get a very detailed point cloud. Here, we use COTR to track the facial landmarks, and surprisingly, it works well on deformable objects, such as human faces. We also apply COTR to Optimus Prime to track its grill, and it successfully tracked it under a very complex transformation. To conclude, first, sparse and dense correspondence problems can be formulated with a single framework. Second, we only train COTR once and can apply it everywhere. Third, that data can be used for explicit correspondence supervision. Thank you for your time. And our code is also online. Check it out with this URL.